Welcome to Introduction to Structures. This is Lesson 9, Stresses.
We have been studying in previous videos the resolution of simple supported beam and cantilever beams in terms of reactions, in terms of internal forces as well. These internal forces were basically the bending moment diagram or the bending moments, the shear forces and the shear force diagram, and the axial forces and the axial force diagram. Once we have defined the reactions of an structure as a simple supported beam or cantilever beam and the internal forces, the next step in the analysis is the analysis of the stresses. There are different types of stresses depending on different situations in terms of how the loads act on the structure. And basically, what we have to study in this introduction to structures are 4 different cases. So we have 4 structures. The first one you can recognize easily that is a simple supported beam because this will be the external load and this will be probably the reactions. We have a structure that is subjected under compression. You have this structure that is subjected to tension, and you have this structure that is subjected to shear forces. After the application of the forces, you will have deformations in your structure. So here we see the deformation produced by these loads. The first case is what we call a bending situation, because this is a simple supported beam and it's subjected to this force which is perpendicular to the beam, to the neutral axis you can see here of the beam, and it's producing this bending, this sagging that produce internally the internal forces we have studied already, the bending moment diagram, or the bending moment, the shear forces and the axial forces if there is any horizontal force. And because of these internal forces, there are stresses on every cross section. And for example, in here you can see that there is a linear distribution of stresses with the maximum on top and at the bottom of this particular cross section in the middle of this beam. We are going to study in more details this distribution and the values of these stresses. In the case of the shearing is you have shear forces that produce this relative displacement between these 2 parts of the structure, and on these cross sections we have a different distribution of the stresses that are shear stresses. The shear stresses have a distribution that follow a parabolic function like this, so the maximum shear stresses for an structure are in the middle of the cross section. So you see the difference between the bending stresses, which have linear distribution in here with the maximum on top and at the bottom, and the shear stresses, which are a parabolic distribution of the stresses with the maximum in the middle of the cross section. When we have axial forces acting on a structure, as in this one, for example, and these axial forces act exactly on the center of the cross section, a type of axial compression stresses are produced, and the distribution of these stresses are constant. So this distribution of the stresses is a constant distribution, so the value of the compressive stress is always the same, and is essentially different to the previous cases. Again, for the bending case, we have a linear distribution of stresses with maximum on top and at the bottom. With the shear stresses, we have a distribution which is parabolic and the maximum in the middle of the cross section. For axial forces in compression, we have a constant distribution of the stresses with a constant value everywhere in the cross section. When we have tension and the forces are applied as well in the same line as the neutral axis, this axis you can see here, you produce a positive stress, and the distribution of these stresses are constants as well as in the case of the compression. So the 2 axials situation are compression or tension, negative or positive, but the distribution of the stresses are constant. As you see as well, the bending has different signs, and we say that the positive sign corresponds to tension, and in this particular example the tension is produced under the neutral axis because there is elongation of these fibers in here, as you can see, And this elongation will produce a tensile stress, and the maximum will be at the bottom. On top, because there is a contraction of the fibers, you will have a linear distribution of compressive or compression stresses, and the maximum will be on top of the cross section. The shear stresses can be positive or negative as well. We are going to see in more detail how we are going to define this, the sign of this stress, and everything will be more clear in a few minutes. So these are the 4 cases we're going to study in this video, and let's do it. So in here I put an example, a numerical example to follow the explanation, and this is a cantilever beam we have resolved before, but I have added an horizontal force in order to have axial forces internally as well that will produce compression in this case, to study completely all the types of stresses you can have in a structure like this. So remember that this is a 2-dimensional structure. So this is a beam, it's a cantilever beam. You have this 20 kilonewton applied in the middle, which is a punctual load. You have this UDL, or uniformly distributed load, of 10 kilonewton per meter, and you have this horizontal force in here of 15 kilonewtons. After the analysis of the reaction, you will find that you have an horizontal reaction equal to 15 kilonewton going to the right. To compensate the force, the external force that is going to the left, you have 50 kilonewtons of reaction in the vertical direction going up that compensates or produce the equilibrium against this 10 kilonewton per meter times 3, which is 30 kilonewton plus 20 kilonewton, 50 kilonewtons coming down. And you have, as a moment, a reaction of 50 kilonewtons, 105 kilonewton per meter that produce equilibrium against the moments produced by these 2 forces in here we have analyzed before. After the analysis of the reaction, we did the analysis of the shear forces, the bending moments, and the axial forces. And as a consequence, we have the 3 diagrams of internal forces with the distribution of these internal forces. So the shear forces have a linear distribution, as you know, under the UDL for a cantilever beam, and the maximum is 50 kilonewtons, the minimum is 0, and the distribution is linear, as you see in here. So we have the values of every single cross section in terms of shear forces because we have the shear force diagram. The same thing happened with the bending moment diagram, but the bending moment diagrams have a parabolic distribution, as you know, because we have an UDL, and under a UDL we have a parabolic distribution of bending moments. The maximum is 105, is negative, and is located in this cross section in here where we have the maximum shear force as well. The compression is constant, equal to 15 kilonewtons, the value of the only one horizontal force applied to the structure, and is constant along the whole length of this beam. So the maximum can be considered in here as well. So we have a cross section where we have all the maximums in terms of shear forces, bending moments, and axial forces. So after the internal forces, as I said before, we can do the analysis of the stresses. The shear forces, the shear internal forces will produce the shear stresses. So the shear forces produce shear stresses, and the distribution, when you have, for example, cross section, which is a rectangle, will be a parabolic distribution. So it's a second order function that will give you the distribution of the shear stresses, and with the maximum in the middle in correspondence with the neutral axis, which is this axis you can see on the screen. The bending moments are the internal forces that will produce the bending stresses, and the bending stresses have a linear distribution with the maximum on top that will be tension in this case because of the deformation that will be produced in this beam, and these compressive forces, which is maximum at the bottom of the this cross section in this particular case. The axial forces, which are internal forces, will produce axial stresses, and these stresses will have a constant distribution. It is to say, the values of the axial stresses will be always the same. We have to remember that when we talk about different forces and stresses, we are talking about different units. And in the case of the stresses, we are going to use unit of forces divided by areas. So many times we are going to use the unit of newtons, over millimeters square. Just to remember, the shear forces are measured in kilonewtons usually, so we have to transform this unit, kilonewton to newtons. The bending moments are expressed in kilonewton per meter usually. We are going to transform this in newton per millimeters when we do the calculations. And the axial forces are expressed in kilonewtons as well, and we have to transform them in newtons to have this a unit of newton per square millimeter when we calculate the stresses. So as I said before in this exercise, and many times it's very interesting or very useful, or is what we look for, we have to identify what is the section in our structure which is under the biggest internal forces. So for this particular cantilever beam, the maximum shear force, the maximum bending moment, and the maximum axial forces are in the same cross section. So definitely for this case, and clearly studying the diagrams, the shear force diagram, the bending moment diagram, and the axial force diagram, this section is the section that is subjected to the maximum internal forces. So this is the cross section more that we are going to study more details in terms of stresses in the first place. So in order to study the stresses, we need to define first the shape of the cross section. In this case, it's a rectangle, and we need to calculate the area, and we need to calculate the moment of inertia regarding the axis X, because this is the axis against the cross section will rotate because the bending of this beam. So the area of this cross section, which is 20 millimeters width and 50 millimeters height, is equal to 1000 millimeters square. As you know, because it's a rectangle and because the barycentric axis is corresponding with the barycenter, which is in the middle of the cross section, the moment of inertia will be B times h cubed divided by 12. B is 20, h is 50, so cube divided by 12, and the value of the moment of inertia Ixx is equal to 208,333 millimeters to the fourth. We have what we call the geometrical properties of this cross section. After that, we are going to proceed to the calculations of the maximum shear stresses. So we know that the maximum shear stresses are in this position in the middle of the cross section, and we're going to need to calculate the moment of area of this green part of this half rectangular cross section. This is the reason why I put this square in here in green. And this is the barycenter of this square in green, and this is the distance we're going to use to calculate the moment of area. The moment of area is necessary to determine the maximum value of the shear stress. The maximum value of shear stress that usually are expressed with tau, the Greek letter. Tau max is equal to the maximum shear force, 50 kilonewtons, multiplied by the moment of area of this green area, multiplied by this distance from the barycenter to the neutral axis, divided by the moment of inertia regarding the axis XX, and multiplied by B, which is the width of the cross section. Replacing these values, we have to transform 50 kilonewton to 50,000 newtons. The moment of area will be the area 20 times 25, the area of this green rectangle, multiplied by 12.5, the distance from the center to the axis X. And all of this will be in millimeters cubed because there are millimeters, millimeters, and millimeters, divided by the moment of inertia in millimeters to the fourth, and multiplied by the width 20 millimeters of this cross section. The value then of the maximum shear stresses in this cross section and in this beam is 75 Newton per square millimeters in the middle of the cross section in here where I'm showing you in this screen.
In order to calculate the bending stresses for this cantilever beam, we need to apply the formula you can see on the screen. So in the first place, because we are looking for the maximum bending stresses, we are going to feed this formula with the maximum moments. You can see in the bending moment diagram that the maximum moment is 105 kilonewtons per meter. Kilonewtons meter. So transforming these moments in newtons per millimeter, we had 105 million newtons per millimeter. We had to divide by the moment of inertia we have calculated previously in here, which is 208,333 millimeters to the 4. And we need to divide the moment of inertia by this quantity, 25 millimeters, which is the distance from the neutral axis to the top fiber in the rectangular cross section, or from the neutral axis to the top fiber at the bottom of the cross section. This is the reason why you have a plus and minus in here, and this is the final results after the calculation. So the bending stress in compression or in tension will be equal to 12,600 Newton per square millimeters. In this particular case, for this cantilever beam and for this cross section we have defined in here. So the final calculation we are going to do in terms of stresses for this cross section and for looking for the maximum values is the calculation of the compressive stress due to this compressive force in here, which is constant along the whole beam. So we have a compressive force, internal force equal to minus 15 kilonewtons, and it's a minus because it's compression. So it's very simple to establish the value of the maximum compressive stress because it's equal to the maximum compressive force divided by the area of the cross section. So replacing the values and keeping the minus to say that this is, to establish that this is a compressive stress, we arrive to the conclusion that the stress is equal to minus 15 newtons per square millimeters. So an important thing to realize is that the calculations of stresses are made cross-section by cross-section. So we have established previously, and we have all the results in here, the values of the shear stresses, bending stresses, and compressive stresses in the cross-section where we have the maximum internal forces. In here we have the maximum, in the section A we have the maximum shear stress, we have the maximum bending moment, and we have the maximum compressive forces, internal forces. So in this cross section we have established these three values for the stresses. So we have 75 newtons per square millimeter of shear stress, 12,600 newton per square millimeter of bending stress in tension and compression, as is shown in the scheme, and a compressive stress of minus 15 newtons per square millimeter, all corresponding to the cross section A. But let's say we want to establish the values of these stresses on other cross sections, for example, the cross section that is at 1 in here. So in order to run the calculations, we are going to fit our formulas with these values of shear internal forces, this value of bending moment, and this value for the compressive forces, because we are talking here about the cross section at 1. This is the reason why it's important to keep the scale of all our diagrams to and we need to keep aligned these diagrams in order to find very easily the values of these internal forces that will allow us to calculate the internal stresses. So for this particular cross section, the cross section at 1, these are the values I have calculated with the formula for the shear stresses, 53, for the bending stresses, 4,950, and for the compressive stresses, minus 15. You can do this with every cross section in your cantilever beam or in any other beam. So for example, if you try to establish the value of the stresses at the section 2, you realize that you need to use this value of the shear internal forces, this value of the bending moment, and this value of the compressive forces. Because the bending moment is 0 at the cross section 2, evidently the internal bending stresses will be equal to 0 as well. So in this case, in the cross section 2, we have only shear stresses and compressive stresses, but we have no bending stresses because the bending moment is equal to 0. Finally, if we want to calculate the stresses after the point of application of this force of 20 kilonewtons, the cross section 2 prime, we realize that in there the shear force is 0 because we are here now, the bending moment is 0, and the only internal force we have is the compressive forces in here equal to minus 15 kilonewtons. So the only stress we are going to have after calculations is the compressive stresses. The shear stresses and the bending stresses will be equal to 0 for this section. And the same thing will happen with every cross section from 2' to 3, because the situation is exactly the same. So no shear stress, no shear forces, no bending moment, only compressive forces applied to these cross sections. So as you see, the value of the stresses are calculated cross section by cross section. So you need to establish the value of the internal forces first, shear forces, bending moments, and axial forces that can be compressive or in tension. And after that, you have to fit the formula. You have to establish the value of the shear stresses, bending stresses, and axial stresses. So this is all. Thank you very much.